Alright, hey, so in class I keep saying things about putting code into the simulator and playing with it and exploring these different concepts using the simulator and so on. And I tell you things like, watching somebody do this or reading about it will not teach you these concepts nearly as well as actually working with them. But, I understand that that doesn't necessarily mean a whole lot to many people. I'm kind of a weirdo. I spent a lot of my life playing with this stuff. This is what I did in school instead of, my classwork for other courses. I would sit down and I would play with this stuff. But not everybody, is in that situation. So let me show you some examples of what I mean by putting stuff into MPLab and playing with it. Okay, for example, the timer 2 register. We know timer 2 is a little bit different from the other timers because timer 2, the timer register starts from 0 and counts up until you get to the value of PR2, the period register, and then it rolls over. The other timers, remember, count up till they hit, 256 or 65,536, and then they roll back to 0. So here's some really short sample code. I'm going to basically put 10 in the period register, clear timer 2, turn the timer on, and just start looping. So I'm going to build that, I'm going to run it, I'm going to look at the timer 2 register down here, and I'm going to start single stepping. So timer 2 is 0, it's 0, it's 0, it's still 0. The timer has not been turned on yet until I do this bit set instruction. Okay, now the timer is on. I'm about to execute one instruction. We might think the timer register would increment to 1, but in fact it increments to 2 because even though we did one instruction branch, it took 2 instruction cycles. And it's instruction cycles that are incrementing the timer register. So another branch, this will increment to 4, another branch to 6, and then 8, and another branch will increment it to 10, which you might think will roll over, but it doesn't. Even though it's equal to PR2, it did not roll over back to 0. But the next cycle it will, and the second cycle after that it'll increment to 1. So now it's going 1, 3, 5, 7, 9. And then it'll increment to 10 and 0, 2, 4, 6, 8. Alright, that's a very simplified analysis of what's going on with timer 2. But the branch being 2 cycles might be a little confusing, so what can we do? Well, let's just change our analysis code a little bit. So I'm going to put in a whole bunch of no-ops instead, because we know no-ops take a single instruction. So let's build that, let's start it, let's single step. And now we're at our beginning no-op. Our timer 2 register is 0. Now it's a 1. It's a 2, 3, 4, 5, 6, 7, 8, 9. It makes the value 10, and then it resets to 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then back to 0. 1, 2, 3, 4, 5, 6, and now it's going to do a branch which takes 2 cycles, so it jumps up to 8. Alright, so now we're getting an example of the timer register, the period register, and also how these instructions correlate to the number of instruction cycles. No ops taking 1, branches taking 2. And we learned something cool about timer 2, which is that timer 2 will actually increment up to and including the value PR2, and then it will roll over back to 0. Alright, so that's some sample code using timer 2. Let's continue this and let's look at the effect of pulse width modulation. I've made a few changes to this code, not a whole lot. I'm putting 7F into ADCON 1 because I'm going to output on RB3. Okay, I'm also going to clear bit 3 of TRISC-B, so say port B, bit 3 is an output bit. I'm setting up my CCP1 configuration register to my magic number hex 0C. If you look at the configuration register, that's a pair of 1s in these 2 bits, and that pattern 1100 says we're doing pulse width modulation, and it's called active high. So if I set up the system for 30% duty cycle, it's high for 30% of the time. If I did active low, it would be low for 30% of the time. Okay, so these are just nuances in how you can configure the system. I put a 5 into CCPR1L. That's my high part from our pseudocode in class, right? That's how long I want the output to be high out of the entire period, which I'm setting to be 10 in this case. and then I clear timer 2 and I turn on the timer, and then I'm going to go through my loop. And I'm looking at port B, timer 2, but I'm also looking at CCPR 1L. Okay, that's the high part. That's how long I want my output to be high. So let's build this code, and let's run it, and let's start stepping. So we get into our loop, and the data sheet will tell you that you have to go through this range of values for timer 2 once before it starts generating PWM output. I'm not going to worry about that. I'm just going to step through the first few steps. So when timer 2 overflows to a 0, guess what? Bit 3 of port B turned to a 1. And you can see it right there. So my output signal is high. After another instruction, it's still high. Third instruction, still high. Fourth, still high. Fifth, still high. And then after the next instruction, it goes low. And it stays low until I hit my period register. And then timer 2 rolls back to 0. The output bit goes high again. And I'll stay high for 5 cycles. And then go low. So this looks like a 50% duty cycle. Let's play with our logic analyzer. Let's go into Window, Simulator, and bring up our logic analyzer. We'll configure it, and we'll say, show me the value of RB3, because that's the output pin. And let's just keep stepping. And sure enough, that looks pretty much like a 50% duty cycle. Alright, now what if we had set CCPR1L to be something like 2? Instead of loading a 5 into it, we could load in a 2. Okay, sometimes this can get you into trouble with the simulator, but we're just going to play around with this, right? I'm just going to go in here and I'm going to change this value to a 2. And I'm going to keep stepping my code. And sure enough, the hardware is generating what looks like a 20% duty cycle. What if I made this a 1? Keep stepping the code. Now we're like a 10% duty cycle. This output is barely high at all. It goes high very briefly and then it goes low again. Now we can get that by looking at these outputs, but the logic analyzer is a quicker way to visualize what's going on sometimes. And if you're used to using it, it can be a big time saver. Okay, on the other hand, what if I load a 9 into here, so a big value? Well, my output is mostly high. It's a 90% duty cycle. Alright, you can read about this. You can watch videos of me talking about it. You can go to websites and get into conversations about it. None of that is going to match the experience of actually doing this. Right? And being able to conduct the experiments that occur to you. Right? Because only you're on a unique path, right? Everyone's on a unique path, and what does that path look like? I don't know. For me right now, it was, let's put this code in, let's look at it on a logic analyzer, let's do a 50%, and then 20, and then 10, and then 90. For somebody else, it will be totally different. It will be, I really want to know what happens if we change the period register. So I'm going to put the period register in here. And I'm going to change it, instead of being 10, I'm going to change it to 100. And I want to see what that does. I'm going to clear out my display, and I'm going to start stepping. And I'm going to very patiently step through all of this. And you can see our timer 2 register, it's up to 80, it's up to 90. When it gets to 100, it'll overflow, and there's our output signal. So period register of 100, CCPR1L of 9, that's about a 9% duty cycle. Right, set this to a 1. And let's just go ahead and run for a while and then pause. And here's our output now. So let's clear this display and single step. And there's our 1 pulse. It was high for 1 instruction. And we're just going to keep going. There's a keyboard shortcut for this, but it doesn't work on my system because I have my keys remapped. So timer's up to 90, it's coming up to 99, 100. It rolls over, there's our next output pulse, and it goes low. There's a 1% duty cycle. So you can experiment with this. You can play around with the values. You can see what's going on here. You can make changes. And all of it is good experience and good practice. And it gets you more familiar with the tools, more comfortable working in this environment. This is going to work really well for you, whether you're doing EE or computer science or computer engineering. You've got to be able to dig into systems, get down to the lowest levels, and analyze them, figure out what's going on, set up little experiments, come up with hypotheses, come up with ways to test those hypotheses, make observations, adjust your hypotheses, and go on from there. That's engineering, that's creative discovery, that's computer science, right? So all of this is like useful. This will help you in your other courses. This will help you in your job. Even if you never touch a PIC processor again, even if you never look at MPLab again, it's the process, right? And it's the knowledge that you can do this, and it's the willingness to say, you know, what I would like to see is this, and then putting together a test case to explore that, and seeing what happens. Right, so this is like all good stuff. This is the kind of thing I mean by, you know, jump in there and get your hands dirty, play around with this stuff. And MPLab is particularly good at this. It understands most of the timing. It understands interrupts, so you can come up with lots of different experiments and play around with it. So anyway, that's just an example. If it's helpful, great. If not, don't worry about it. We'll find another way. All right, thanks. Bye.